the two-body problem, well, we've been discussing singular particles our whole lifetime, but the time has come to realize that there is more than one particle in the entire universe. Fortunately for us, unfortunate for our studies. Which means that we have to come to grips with the fact that unlike classical particles, quantum particles are totally indistinguishable. Now, in the moment, if you look at them once, you can say, oh, this particle is in one state, this particle is in the other. We've distinguished them. Unfortunately, if you observe them, you might just be changing their states, which means you can't keep track of which one is in which state over time. It's like if you have a red ball and blue ball and you shuffle them. You can tell that, oh, the blue ball was over here, the red ball was over there, and now they've switched places. But if the red ball constantly changes color every time you look, and the blue ball also changes color every time you look, then can you really tell the difference? But it's not just that. While you might be able to follow classical objects, quantum objects, every single time they're observed, because of the uncertainty principle, are going to, they might just change their state. There's a probability of them doing so or not doing so, which means you will never be able to know which one is in which. But there is one good thing that comes out of this. Since we now have to update our wave functions in order to make them symmetrical, because otherwise, reality would break down, our measurements would be totally useless, as one could be for this version of reality, another could be for that version of reality, and all the versions of reality created by the differences in permutations of the particles in certain states. By the Pauli exclusion principle, if you have two particles in the same state, the wave function that we constructed just for them to solve the Schrodinger equation, for more info on that, watch the full lecture, is going to collapse. It's going to become zero. And non-normalizable wave functions can't exist in the real world, which means two fermions in specific can never take on this. Two identical fermions can never take on the exact same quantum number. Otherwise, everything collapses. Everything dies. And so, that is what today's lecture was all about. Identical particles. That's it for today. Thanks everyone for watching, and we'll see you in the next one.